This data-driven map plots the extent of the Indus Valley Civilization. Emerging around 3500 BCE, it stretched from Balochistan to the Ganges. At its peak, this footprint covered nearly 1.5 million square kilometers, dwarfing every other Bronze Age society. When archaeologists examine early human societies, they typically look for a specific type of architecture to indicate complex organization: grand tombs, colossal temples, or massive royal palaces. The ruins of the Indus Valley lack these structures. There is no evidence of autocratic, monumental architecture built to glorify a single ruler. The defining feature of these cities is rigorous municipal standardization, visible in the sprawling, highly organized civic landscapes that remain today. This standardization is concentrated in two primary domains: rigid urban grid planning and complex water management. Executing and maintaining high-precision infrastructure across a continent-sized territory required a specific logic, one that functioned without the centralized authority of a traditional dictator. To understand that logic, we are going to reverse engineer their systems, rebuilding a Harappan city using a first principles approach. Analyzing the macro-scale city requires starting with its smallest micro-component. The architecture suggests a society where sophistication was directed toward collective utility rather than individual monument building. The bedrock axiom of Harappan engineering is the fired clay brick. This illustrates the exact dimensional ratio used by Indus Valley builders. Its proportions were kept strictly at a 1:2:4 ratio of thickness to width to length. That mathematical geometry is optimized for structural stability, allowing the bricks to interlock smoothly in an alternating bonding pattern. This exact dimensional ratio remained consistent across thousands of kilometers and dozens of diverse settlements. Producing fired bricks is a volatile process. Without strict oversight, variations in clay moisture and kiln temperatures naturally yield irregular sizes. Achieving this level of uniformity across a 1.5 million square kilometer area implies a centralized system of weights and measures. The standardized brick provides physical evidence of an administrative intelligence capable of enforcing quality control across an entire subcontinent. Scaling up from the individual brick, these uniform materials translate into rigid geometric layouts at the macro level. Major centers like Mohenjo-Daro and Harappa were defined by a strict orthogonal grid system. This top-down wireframe maps that geometry. The main arterial streets intersected each other at 90-degree right angles. Most early human settlements grew organically, expanding outward in uneven or winding patterns. The Harappan plan is a deliberate departure from that model. An organic city grows by reacting to immediate needs. An orthogonal grid is predictive. Laying down a perfect grid requires advanced surveying and mathematical pre-planning before construction begins. The implementation of this layout shows that Harappan engineers prioritized municipal flow, traffic, and infrastructure over short-term expansion. That rigorous geometry extended from the street layout above ground to the subterranean hydraulic systems beneath. This cross-section reveals a closed drainage network. Unlike later open sewers, the Indus Valley built covered channels. Inside the home, wastewater flowed from washrooms into dedicated domestic chutes. These chutes fed into the gravity-fed flow of the sealed municipal channels running beneath the streets. The system included built-in access points spaced at regular intervals along the enclosed drains. These functioned as manholes, designed so maintenance workers could clear blockages and ensure long-term functionality. This network represents a systems approach to urban living, where public sanitation was engineered as a standard baseline. The ultimate test of this hydraulic engineering is Mohenjo-Daro's Great Bath. This model illustrates the structural challenge, containing massive volumes of water without allowing seepage to erode the fired brick foundations. The solution was a waterproofing membrane sandwiched between the brick layers. They utilized bitumen, a naturally occurring heavy tar. Bitumen creates an impenetrable seal, providing a watertight barrier that prevents fluid transfer into the surrounding masonry. Securing the Great Bath demonstrates a mature understanding of material science applied to fluid management. Viewing the archaeological site at scale reveals a single interconnected machine. This macro-scale view synthesizes the two systems. When the street grid and the subterranean drainage networks operate together, their relationship is clear. A gravity-fed covered drainage system is impossible without a geometric street grid to dictate its slope and direction. The two systems are codependent. Around 1900 BCE, this machinery began to fail, and the cities were abandoned. Climatic shifts caused severe droughts, and the massive Indus River system altered its course, collapsing their supporting ecological system. This environmental catastrophe led to the complete evacuation of the cities, and this municipal technology was lost for millennia. The precise administrative records that governed this society remain locked away, written in a script we still cannot decipher. The Indus Valley Civilization shows that rigorous urban planning, mass standardization, and public sanitation were successfully engineered at a macro scale thousands of years before the modern era.